everybody. My name is David Barron. Apologies, my Arabic is terrible, so I'm going to have to present in English today for you all. I am a chartered structural fire engineer, and it is a pleasure to present to you all today the first FireX in Egypt. So today I would like to talk to you about fire protection for steel structures using passive fire protection. So it's going to be a slightly different topic from, say, sprinklers or detection. I'm going to go into why this is so important in life safety strategies in buildings. So to start, I'd like to talk about fire and how it develops in a compartment. So at first there is an ignition, and then the fire grows. And at this stage, this is where you will have detection using your detection systems, as well as likely sprinkler activation to limit the growth of the fire. However, at some stage, that fire could reach flashover conditions. And all this means is the temperature within the compartment has got so great that all combustible materials have now ignited. And this is dangerous for the structure of the building because you now have a fully developed fire. After the material has burnt, you also get a decay phase. So this is where you can get a lot of damage to your structure. And that's what we want to limit using passive fire protection. So what we're trying to do in high-rise buildings is make sure the occupants can escape. So I'm going to talk about two things here: available safe egress time and required safe egress time. So when we're talking about available safe egress time, we want to increase this measure. So sprinklers will limit the development of the fire. Smoke control will remove the smoke so that people can evacuate the building. But more importantly, in high-rise buildings, if you were, for example, in the Burj Khalifa and the fire reached a fully developed state, you want to ensure that that fire stays in the compartment of origin and that it doesn't affect the stability of the structure. So that's what I'm going to talk to you about today. So the structural stability using passive fire protection. Now, passive fire protection is a vital component in any fire safety strategy. It's there to safeguard people's lives and limit the financial impact and damage to the building and their contents. So one way it can do that is to limit the spread by containing it in a single compartment. We also want to protect the escape routes and make sure that people can escape from the building. But also, we need to protect the building's structure because all materials lose strength at elevated temperatures. And when we talk about fire resistance, what we're talking about is resisting structural collapse, so the building will actually stay stable. We want to resist the passage of smoke and hot gases, so we want to contain that, as well as resisting the heat conduction, so that no heat transfers out of the compartment into other areas. And today I'm going to talk solely about the stability requirement, so just structural stability. So steel is quite a popular building construction. As you can see in this building, we have a steel roof construction. We build a lot of stadiums, a lot of high-rise buildings. One second. Sorry. And so we build a lot of large high-rise buildings, infrastructure, stadiums, railways, airports out of steel. And there's a selection of steel sizes we can use. Apologies. So there are many steel sizes we use as engineers, from I-sections, hollows, cellular beams, to construct these wonderful structures. The problem with all building materials is that they lose their strength at elevated temperatures. So in the event of a fire, they are going to start to become weak. And that's no different for steel. On this axis here, again, second. So on the left axis here we have 100% strength retention and 0. Just continue. Thank you. So, steel loses strength at elevated temperatures. I will just continue through, I'll speak louder. So steel loses strength at elevated temperatures. At 20 degrees, it will have 100% of its strength. But in the event of a fire, at 550 degrees, this is the steel temperature, not the fire temperature, it will have lost 40% of its strength. As the steel continues to increase in temperature, it continues to lose strength. At some stage, that steel will not be able to support the applied loads, and you may get structural collapse, or you may get a breach in compartmentation, which will breach the fire safety strategy. So it's important that we protect steel and other structural elements from the effects of fire. And there have been many tests done to show the effects of fire on unprotected steel and other construction elements as well. So there are two main fire types that we see, cellulosic and hydrocarbon fires. Cellulosic fires are the one I'm going to discuss today. So that's materials like textiles, wood, paper. You don't really see hydrocarbon fires in high-rise buildings, but it's nice to be aware of it. And what we do in testing is we try to emulate that fully developed fire. So we're only worried about post-flashover conditions. So we have time and temperature. And we get up to about 1,100 degrees after 2 hours in the fire tests. So this temperature rise needs to be limited. And this is to prevent the structure from losing its stability in the event of a fire. And there's really good reasons to do it as well. Personnel protection. If we were in the Burj Khalifa or any other high-rise building, we'd want to get out with our families safely. And also, we want to ensure that the emergency responders can come to the building and deal with the blaze safely, knowing that it's not going to come down. Buildings cost a lot of money as well, so we want to ensure that we're protecting the buildings and we can reuse them after the event of the fire. And finally, it's legislation. So legally, we have to provide fire protection to these structures. And there's a number of ways that we can provide the insulation to steel. There's a few examples here: board, cementitious, and intumescent. And I'm just going to go through those three types very briefly with you now. So boards, these are preformed rigid panels. The boards forms boxes around the steel elements, and they're usually either fixed mechanically or by gluing. And these are used for very technical profiles and form a constant section. Where you need site cleanliness as well, where you don't want much dust or damage, these are a perfect system. However, it can be slow to apply, and these don't offer any corrosion performance. Steel corrodes, so we need to protect the steel from corrosion as well, because most days it won't be seeing a fire scenario. Also, we have sprayed materials such as cementitious, gypsum, vermiculite and perlite. These are very cheap and effective systems, but often hidden due to their poor aesthetics. These can be 15 to 50 millimeters required on steel, depending on your fire scenario. And again, these don't offer you corrosion performance either. And the final system that I would like to talk to you in a bit more detail about are intumescent coatings, which are reactive. So these apply very, very thin onto your steel using a spray gun or brush applied. They have much better aesthetics than some of the other systems and can be applied both on-site and in shop. So they can actually be applied at fabrication yards and shipped to site pre-fire protected. There's also systems that are damage resistant, and you can get very, very fast application. Also, these systems do offer the corrosion performance as a system. The only downside to these systems with some of the current technologies is they can be quite expensive at the higher durations, which is what you typically see in high-rise buildings. although engineering principles do allow you to optimize that requirement. So the intumescent coating will look like any decorative paint, but in a fire, it will expand to 50 times the thickness it was applied at. So it is quite a change when it sees fire. And this char that you see here, that will insulate the steel from the fire. But when there isn't a fire, you wouldn't even know it was there. Probably very similar to what might be on this roof structure here today. And the principles behind how it works, we discussed how a fire develops, and there are very, very well documented fire curves that we test to, trying to copy a fully developed fire. And if we did nothing to the steel, it would heat up very, very quickly. And in fact, it might reach its critical temperature, or the temperature at which it would lose its load-bearing capacity, within about 10-15 minutes. That isn't enough time to evacuate high-rise buildings or many infrastructure buildings. So we apply these thicknesses of intumescent that react and then protect the steel for the given amount of time. So that's the sort of fundamentals behind passive fire protection and intumescent coatings. If we have a fire, there are only 3 things we need to determine the thickness of an intumescent coating. This isn't the fire triangle, by the way, this is section factor. We need to know the dimensions and the proportions of the steel elements. We also need to know at what temperature will that steel collapse. What temperature will it no longer be able to maintain its stability? And finally, how long do you need that building to maintain its stability for? If you've got a small warehouse, maybe 60 minutes. But for a high-rise building, it's going to be closer to 2-3 hours maybe, just to ensure that people can evacuate. And once you have those 3 parts of the information, you can determine a thickness. So I'm just going to briefly go through these 3 elements at a very high level, just to give you an appreciation of what these are. So the fire resistance period. So this is basically determined in minutes. How long must the building maintain its stability in terms of fire resistance? So durations are typically 15, 30, 60, 90, 120, even 3 or 4 hours, depending on the occupants, the height of the building, and which legislation you're using locally. And the purpose of setting a fire resistance period is to ensure that in the event of a fire, everyone can get out of the building and that the emergency services can get to the blaze and deal with it. So that's resistance period. The section factor, this is all related to how quickly steel heats up. And it's all to do with how much of that steel is exposed to the fire and how much surface area it has. I think you can all appreciate that a steel element like this will heat up a lot quicker than a very, very stocky section like this. So we don't have to apply as much thickness to this element as this element for the same duration. So we need the section factor as well. And finally, at what temperature will that steel fail in the fire conditions? Now there's 2 ways of doing this. There are prescriptive values laid out by legislation that you can just adopt, and you don't have to do no structural checks. You have done what's legally compliant. This can sometimes be quite conservative, and there are fire design and engineering approaches available to us, code compliant, that allow us to optimize this requirement and ensure we're applying robust levels, but actually based on the applied structural loads. So I'm going to finish up with a couple more slides and then I'll leave you alone. This is a table that we generate from all the testing we do of our intumescent products. You can see a fire duration, a temperature, and the section factor. And all we do is we look at the legislation. It requires 120 minutes, say for a high-rise building. We can calculate the section factor, say for 120, because we know the geometry of steel. Steel geometry is very well known, we can calculate that. And if we look at then a table of prescriptive temperatures, we can find the exact thickness we need for that fire scenario. And in this case, it would be 2.847 millimeters. So this is where all the thicknesses for all the steel elements come from. It's by doing this process. And just in case, there are a few technologies available with intumescent coatings. There are water-based, solvent-based, and epoxy-based. Now, they all behave very similar in fire, but they have very different corrosion properties and very different application properties. So the intumescent will not see a fire every day. It's got to sit there, be decorative, and got to provide the corrosion performance. So it is very important to pick your technology correctly when specifying. And just final thoughts from me. Passive fire protection is a vital component in any fire strategy. It's there to safeguard lives and limit the financial impact and damage of fires. When these things are correctly specified, passive fire protection can not only provide the needed fire resistance period, but it can also offer an aesthetically pleasing finish whilst also providing the corrosion performance we need in our structures. So I would just like to say thank you, shukran, for listening to me. I look forward to seeing you at the conference.
Thank you very much, David, for this interesting presentation. For many people, it's new. There is a question here, ground floor.
Thank you for a perfect presentation. And my question is, when we are working with the fire dynamic simulations and modeling, shall I put the area to volume ratio in a high-rise building for the affected zone or for all the building, considering that this ratio completely changes from ground to up?
I totally agree, and this is one of the problems I think with the industry, that we do all this great work in calculating the fire size, the temperature rise, the smoke movement, and then it comes to manufacturers and all we do is we turn it to that fire there.
This is perfect curves. We can put it inside the program.
Yes.
But I have a construction under design.
Yes.
Okay, and it's totally steel structure. Okay, at the ground up to the 10th floor, you will find the area to volume ratio of the steel will not exceed 5.6 or 6, whatever.
Okay, yes.
All right. When you go up for the 30s or 40s floor, it's reduced completely. So, shall I take all the building, or I considered only the zone where I thought that the fire will, according to the fire scenarios? I mean, okay.
And so you're talking about the steel sizes themselves?
Yes.
When we're manufacturers and when we do design work, we will work with whatever steel size is there. So we don't recommend converting all the steel sizes into bigger ones, although that does actually provide a cost-effective solution.
Sure.
So we would calculate for every profile individually.
Each floor, for example.
Each floor.
Each fire zone.
Each fire zone, each duration, we do that per floor. And it gets quite complicated in terms of application, but I think this is where BIM and building information modelling can really help, where we can actually map the thicknesses, the fire protection requirements, all on the models that we're doing, so we're making sure that it's all correct.
Okay, thank you. Another question. Regarding the protecting material, is there any lifespan for it, or it's the building life?
Yes, some of them, it depends on the corrosion environment. Depending on the technology, they will last longer, but usually we'd expect like 25 to first major maintenance. But if you're in a building like this, the system should last for the full lifetime of the building. It shouldn't degrade at all, it should still function. So as long as it's not sat next to the sea, outside, it should be fine. So again, this is something about the correct specification. We need to know where the building is, the corrosion environments, and making sure the system is adequate and will provide the protection through the lifespan of the building. Exactly, is that okay? Thank you very much.
Thank you very much. May I put a question? We say that you are going to paint the steel by the material. Does this mean that you have taken into consideration that the steel have a space enough around the steel structure itself? Otherwise, you are going to lose the distance of expansion?
Yeah, the expansion zone is actually under research at the minute. So obviously these coatings expand.
Yes.
If you look at, say, non-fire rated plasterboard, there's test evidence to show it just burns away. So it leaves it freely exposed.
You have to leave it free.
So if it's
far
not,
a little bit from the...
so you can space materials out if they're fire rated. But if they're fire rated and it'll expand, then that fire protection material that might act in lieu of the intumescent. So it's an area of research, and it's something that's been done quite heavily in the UK, and once that guidance is available, I think we'll be sharing it with everybody. Yes, it's a good question.
Thank you very much.
No,
Thanks
thank
a lot.
you very much.